X, then capital Y, no? So he says there are many ways of saying this thing. He says one is Y if X, no? Y if X. Other one is X only if Y. This one is kind of, we are uncomfortable with English. X only if Y means if X then Y. No? Then if you take if X then Y and if Y then X, let's try to connect these two. One is X, we can say Y, if Y then X, Y, X if Y, no, X if Y, this line. He says he is not comfortable with this norm in the sense that he says you have to think for a while. And X if Y, but what is amazing about our A-level exam is this thing is used in A-level. If X if Y, then this one Y only if X. Am I right? This one? I also get confused. Let's see. This if Y then X, X if Y, that is true. If X then Y, then X only if Y. X only if Y. So can you see here, X if Y, X only if Y, then we combine these two X if and only if Y. X if Y and X only if Y. So that is how this X if and only if came. That's how it is. We get X if and only if Y. I don't use this one actually when I teach or when I write or in the books I have written, I guess I have mentioned it. I say I don't understand. Something I wanted to. He doesn't, even before introducing this X implications, he talks about this. So it's kind of, according to me, unfair, but what to do, no? That's the way he is. Yeah. Okay, so there may be many other things that I will bring on the way, the course about logic, because you have to have a very good feeling about logic in order to understand analysis. Algebra actually, I guess, you can do without logic. In fact, I wanted to write a book in algebra. Good morning. Did you bring Lalitalapa or something? No, because you are getting late. They were saying maybe you are on the way to buy some Lalitalapa, Munkav, something like that.
I was in the bank.
Okay. Then you back?
I was in the bank.
You in the bank. Oh, then we can have ice cream. You went to the bank. Kutari mentioned this thing a little bit here. If X then Y, we can say Y if X, and X only if Y also, if X then Y. then if x then y, I can say x only if y. If y then x, I can say x if y. Then I connect these two. X if y, x only if y. Here, two statements here. X if y, x only if y. And it's connecting. Logical, and is here not the English and, it is mathematics. Our logical connective and X. So that we abbreviate I double F. If and only if is abbreviated by I double F. If and only if Y. So now we are going to do this chapter. Actually, chapter 1 in this book is sort of a motivation for the, to mathematics, because there are so many mistakes that we can do, we may do, we do actually, not we may. Because if we don't give the correct reasoning, so he has so many examples, that's very good one actually. But the thing is that if I write a book, I write examples that the students can understand. He writes the book which are correct, even if you don't understand, it is there. So there is a difference. Then here in chapter 2, can you see, sometimes we say, for instance, when it comes to congruence of triangles, we say, if you take two triangles like this, if this side is equal to this side is equal to this side is equal to this side, we say these two triangles are congruent. I mean, it is said that they are congruent. We don't know. We don't know. If somebody asks you, how do you know that they are congruent? You have to say, oh, it is, they say. No? But somebody has proved this. For instance, when I say somebody has proved it, there are axioms. The word axiom is something you cannot prove, but whole world believes it is true. That sort of things are called axioms. One axiom is, if you take 2 points, 2 distinct points, anywhere, doesn't matter where it is. Between these 2 points, they are distinct points, there is a unique line. Nobody can prove it, but it is taken for granted. Because it is true, no? I mean, if you take 2 distinct points, of course, there is a line. So that is an axiom in geometry. Another one, if you take 3 distinct points, not collinear, not in the same line, there is a unique plane through these 3 points. That is another axiom in geometry. Like that, there are some axioms, I mean, nobody will argue about whether they are true or false. It is definitely true. Like that, there are some axioms, using that axioms, it can be proved, because if you take 2 triangles, there are so many things you can talk. No, people say how many things are there, 3 sides, 3 angles. But there are so many, I mean, you can talk about the perimeter, you can talk about the area, you can talk about the radius of this inner circle, you can talk about the radius of outer circle. Like that, so many things you can talk about a triangle, not only 3. Not only 3. So, and another thing is, You take a triangle, you go say half a distance from here, you do this height, and you take the other triangle, again you go to half a distance, you get this height. If these two triangles are congruent, these two must be the same. So many things in two triangles that we can talk, properties. All of them are going to be the same if they are congruent. I myself don't know how to prove it, but of course I have read the proof. I mean, they are proved by using the axioms. Axioms are, you need to keep in mind that axioms are things nobody challenge that they are true. That sort of things are axioms. Then when you are doing analysis, again there are axioms about numbers or real numbers or integers. So that's what we are going to discuss today in chapter 2. I myself haven't done this, he calls them piano axioms. For instance, one result in about numbers is, so when you take any real number, x, actually this is one reason I began to do mathematics. In campus I was told, given any real number x, you take any number, there is an integer greater than this number, x. It is obvious now. You take any number x. There are not only one integer, but there are so many. Then there is a proof. I was so shocked. How on earth you can do this thing? I mean, why should you do it to begin with? I mean, it is of course, it goes without saying. However, to do analysis, you cannot, what you think is true, if you are going to say the things appear to be true, or you think that are true, if you take everything for granted, then you cannot do maths. There is a set of axioms and definitions you agree with. Then from that you try to do the rest. So there are axioms as well as some definitions. Definition means that now my name is Ramasinghe, So that's my definition. That's how somebody will talk about me. Here in this chapter, it is I read this thing. Actually, I read twice. Because the thing is, I myself haven't studied these axioms in this book. But I talked to Dr. Prabhat, I told him certain things here are not that great, but the most important thing is that when you follow this course, you need to say which book you use. If you say, regardless of how good my books are, if you say we use Dr. Ramasinghe's book, who is a elephant book, nobody knows. Of course, in Sri Lanka, everybody knows. But when you go out, you can use my name. Nobody knows. I should say nobody knows, of course, there are some people who know my work for my PhD. But this person is a really well-known person in mathematical world. So that's why we are using this book. Starting at the beginning, the natural numbers. So we are going to give some statements that we can believe that they are true. Not so many. But out of these few statements, you can prove everything about integers you know of. They are called axioms. So, I mean, if you, I myself read, the notes, I did not write anything in my own, by the way, because purposely I did it. We say, as you may know, we use this N. Sometimes I am not happy, but I cannot make myself happy because always we use this N. This is the letter N. As you may know, we use capital N to denote the set of natural numbers. Z to denote the set of integers. This is natural numbers. Integers. And Q, rational numbers. And there is no letter for irrational numbers. See how unfair it is. Before the end of this course, somewhere here, I will, if you take the real line, this one is, length of this line is infinity. I am going to prove either, not from this book, maybe next one, and you have going to study a thing called measure theory. We are going to prove that if you take a very small length like this, regardless of how small this interval is, you can put all the rational numbers here, all of them. All of them. Such that kind of numbers, there is a big place given a suppose set of rational numbers, even there is a letter recognized. But irrational numbers, now I told you, all the rational numbers are here. In the remaining infinite length, all are irrationals. But can you see, there is no letter for set of irrational numbers. How unfair. Injustice is everywhere. Not only in the world. In the world of real numbers, you got my point? To place all the rational numbers, all you need is, actually you don't need any length, we will be doing it. Even now I can do it, but I won't do it because it is not the time to do it. To put all the rational numbers, you need a very small length. Actually we prove that you don't need any length. It will be proved. If you find my book, Sankhyawa Parameyavimi Sambhagata, I have proved it there. It's not difficult at all. But regardless of how small the amount of rational numbers, there is a letter Q for the set of rational numbers. Even though almost all the numbers are irrational numbers, it doesn't have a letter. If I ask you to give me a real number, could you say give me a real number, something you like? What? How about you? 4. How about you, Puta? 7. How about you, Betty?
69. 69.
See?
69.
69. I will say 2 over 3. Do you see how much unfair the world is? When you think of the set of real numbers, almost all of them are irrational. But if you ask anybody, give me an example of a real number, always give you a rational one. Can you see how unfair? It's very unfair. Almost all the real numbers are irrational. But if you ask anybody an example of a real number, nobody will give you an irrational number. What is amazing thing is, most of the irrational numbers, nobody knows. Now, for instance, this number, 0.1, 01, 001, 001, like that, if you write then 4 zeros and 1, you continue. I mean, this is a very nice number. No? You write like, and of course you write this way, no? 0.33333. If you write like this, actually this is equal to 1/3, no? But if this is a very good real number, but can you see, we call it irrational. How rational this number is? Very unfair. Actually, there are some mathematicians did not agree with this, to say that this is an irrational number. This is irrational number. I mean, always 0.1, then 0, then 1, then 2 zeros, then 3 zeros, 4 zeros, 5 zeros, and so on. But the funny thing is, we can prove, and you will be proving this thing, I guess next term or this term, somewhere, that this is not rational. So this is an irrational. We prove that this is not rational, therefore it has to be irrational. So what I am trying to say is, so many things we say in the world it is unfair. No, I mean in South Africa it was black people were discriminated. Here irrational numbers are discriminated very highly. Not like blacks in South Africa. It is amazing, that's the world. So anyway, let's continue here. Q to denote the set of rational numbers and R denote the set of real numbers. This person, according to this book, N is 0, 1, 2, 3, 4 like this. He has included 0 also, but this is the first book I show that 0 is included. I don't include 0 as a natural number. The natural numbers are the most primitive of the number system. This is most primitive one. This is the most primitive. Most primitive. Primitive. Simplest one. Most primitive of the number system. However, using these numbers, we build integers out of them. Integers means this one, no? Positive integers, negative integers, and 0. All of them are integers. Using that set, we build the integers, then which in turn are used to build rational numbers. Using them, again, all are rational numbers, by the way, here. But quite often when you say, another thing is, if I ask someone, give me a rational number, nobody will say 2. Everybody will say 1/3. Because when you say rational, mind thinks about not integers, mind thinks about fractions only. But integers are rational numbers, which in turn are used to build rationals. In addition, the rationals are used to build the real numbers. We are going to learn it in this course. So, can you see, this is the base. It is like when you are putting up a house, base must be very strong. You cannot change the base if it is a 100-story building, you put, after putting up, say, 50 stories, oh, the foundation is not good enough. You cannot go back and change the foundation. So, since n is the foundation, from n you go to, we said, whole numbers, integers, from that you go to rational numbers, from that you go to irrational numbers. So as a result, you need to know about n really well. It is like when you are putting up a house someday, you have to put a very good foundation for your house. Same way here, since n is the most primitive thing, we need to have a very good idea about n. In addition, the rationals are like, hence to begin at the very beginning, we must look at the natural numbers. We need to know about natural numbers really, really well. How does one define the natural numbers? To you, sometimes this may be a little awkward because you came to here to some analysis talking about numbers, how to define natural numbers. I mean, it is taken for granted these are the natural numbers. No? But as an analyst, when you are going to do analysis, if somebody asks you what are natural numbers, you have to have an answer. But if you go to supermarket, you said you went to the bank, nobody will ask, what do you mean by a rational number? What do you mean by integer? It is taken for granted. It's not a question for them, but for us, yes. Especially if you are going to do analysis. This question is far more difficult to answer than it looks. I cannot answer. If you ask me what are natural numbers, the basic problem is that you have used natural numbers for so long that they are embedded deeply into your mathematical thinking. I have taken some statements from the book itself. In order to proceed, very important, in order to proceed, try to set aside for the moment everything you know about the natural numbers. Very important, I am reading it again. In order to proceed, try to set aside for the moment everything you know about natural numbers. Forget that you know how to count. You have to forget, otherwise we cannot continue this chapter. To add, to multiply, to manipulate the rules of algebra, etc. You have to forget everything. You have to assume that you know nothing in order to learn. We will also forget that we know the decimal system. I have written some decimal expansion of a number. We also forget that we know the decimal system, which is an extremely convenient way to manipulate numbers, but it is not something which is fundamental to what natural numbers are. We are going to learn about decimal expansions, but to learn decimal expansions, first you have to understand this. There is a chapter on series. We need to. You have done series in A level, but that's the smallest thing in the world. Yes, it's nothing. Even the definition is not given in A level, unfair. So can you see now we are going to forget everything about natural numbers we know. We don't know anything. You have to forget, you don't know how to count, you don't know how to add, you don't know how to multiply. You don't know, many algebraic things that you manipulate. You have to forget all that. So let's see, then he is talking about the piano axioms. I have taken the most important things from the book. We now present one standard way to define the natural numbers. This is a standard way. In my book also, the books I have written to Open University, I also have done it with not the piano axioms, but in a different way. Define the natural numbers in terms of the piano axioms, which were first laid out by, I cannot read this guy's name, Giuseppe Piano, whoever it is, I don't care. Of course, this is not the only way to define natural numbers. However, we shall stick with the piano axiomatic approach for now. In this book, we are going to learn what are natural numbers, how to play with them using the piano axioms. Then definition 2.1.1, he has informal and uncomfortable. No definition can be informal, but here is a natural number is any element of the set. By the way, when he is defining, you need to notice this thing. When he is defining something, he put this way. So this is not exactly the equal sign. So you get the impression the thing on the left hand side is not known to you, but the thing on the right hand side is known to you. So that which is the set of all the numbers created by starting with 0, okay, and then counting forward indefinitely. We call them the set of natural numbers. So we are going to agree with there is a number called 0. So far that's what he is saying. We agree with created by starting with 0 and then counting forward 0, then count, you go, then you get all the numbers. That is the informal way of talking about natural numbers. You begin from 0, then if you count 1, 2, 3, 4, etc. Remark, in some texts natural numbers starts at 1 instead of 0, I told you that. But this is a matter of notational convention more than anything else. In this course, we shall refer to the set 1, 2, 3. In his case, he is 1, 2, 3. This set he is taking Z plus. That is in this book, rather than the natural numbers. Natural numbers are sometimes also known as whole numbers. Again, in other books, these are whole numbers. But in his case, natural numbers are whole numbers. To define natural numbers, we will use two fundamental concepts. Now we have to be serious. To define natural numbers, we will use two fundamental concepts. One is the number 0. That is this piano axiom method, the 0 number and the increment operation. As an analysis student, you need to do once in your life how these numbers are created. You need to know, but after learning it, thereafter, you are not going to prove anything about addition and subtraction. They will take it for granted. To define natural numbers, we will use two fundamental concepts, the 0 number, 0, and the increment operation, increase. We will use n plus plus. He says we will use n plus plus, n 2 plus, n plus plus, to denote the increment of successor of n. Or increment of n. Because if you are putting plus, you cannot put 1 plus, no? You cannot do like this, then they may think you are going to add. So this doesn't work. N plus plus. So the 0 number 0 and the increment operation. Can you see? Two basic things. Geometry is made of points and lines, no? Geometry, everything is made of, actually, line is also a collection of points, but we usually say points and lines. Like that, these integers are made of 0 and increment operation. So n plus plus, you know, to denote increment or successor of n. Thus, for instance, 3 plus plus is equal to 4. So, I mean, sometimes you may think this is sort of crazy. I should have this plus plus thing instead of writing 1. Anyway, this is piano exam method. I cannot answer that. So he says 3 plus plus is equal to 4. Then 3 plus 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 is equal to 5. Like that. By the way, in my book, I haven't mentioned much. You talk about numbers using sets. Empty set, set with empty set, set with empty set, and the set with empty set. This is 0, this is 1, this is 2. There is a way of doing that. But to do analysis, you don't have to be an expert in any of them, but you have to understand there is a way of doing it. You have to go through them, do the exercises and learn, then forget it. After that you are not going to talk about basic things, then you have to deal with the actual problems. It appears that we want to say that n consists of 0 and everything which can be obtained from 0. N consists of 0 and everything which can be obtained from 0 by increment operation. Obtained from 0 by incrementing. N should consist of the objects 0, no? But I said n consists of, now this is our definition. N consists of 0 and everything constructed by 0 using the increment operation. So you get 0, you have 0, then you have 0 plus plus, then you have 0 plus 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 plus, like that. You get. It is it. Axiom 1. We have to be now serious. I am saying, I told you now, among the things I said, one of the important things is n consists of 0 and everything can be obtained by increment operation successively. And you are going to get an axiom made. So, to master the chapter 1, you need to, I myself wanted the red ballpoint to show you this thing. Anyway, when I come next day, I guess I will buy a red ballpoint and circle it so that you can see well. Okay? Axiom 1. Axiom 1. What is it? 0 is a natural number. You write 0. This is O. This is 0. It's a natural number. I myself cannot, I am very much older than you, but I still cannot write 0. I write always O, 0. If somebody asks me to write 10, this is how I write. Actually, it should be 1, like ellipse-like thing. I mean, these are important. Some places. Axiom 1, 0 is a natural number. So, we take it for granted that 0 is a natural number. Then axiom 2, very important. If n is a natural number, then n plus plus let me make it short. Then so is n plus plus. You have, I did not give you these phases. No? So 1, 2, 3, 4, say 5, 6. Yes, I have many things I did not write in my own. They are from the book, but kind of important things. You cannot keep everything. Now you cannot ask questions. Why 0 is a natural number? You have to take it for granted. 0 is a natural number. Then he says if n is a natural, this may be a little funny to you at the very beginning because the things you know about integers, I guess as much as this professor knows. You know, so why on earth you are going to study this? But to develop analysis, it's very important that you have to have a firm idea that everything can be proved. That is the goal here. If n is a natural number, then I guess let me put then also. Then so is n plus plus. What it means is if n is a natural number, then n plus plus is also a natural number. From that, since 0 is a natural number, you know 0 plus plus is a natural number. Then 0 plus plus, then plus plus are natural numbers. So now, what is the most important thing? You have two axioms. You have two axioms. 0 is a natural number. You agree with that. Then, if n is a natural number, then so is n plus plus. Now we are going to get a definition. Definition is, I guess, singular word for definition is after the agreement. So it says meaning actually. We define 1 to be the number 0 plus plus. Let me write it because it is important. We define 1, this one, to be the number 0 plus plus. What you know is 0 is a natural number from axiom 1. Then from axiom 2, you know if n is a natural number, then so is n plus plus. This 0 plus plus is a natural number. So actually 1 is equal to 0 plus plus. That's what it means. So good thing about this person is he writes English. Even last night I was telling Dr. Prabha, I don't know any professor in the world who writes this much of things. And actually, when I read other maths books, I know all the words in those books. But when I read it, sometimes I have to go to dictionary. I don't know the meaning. It's good in a way. So we define 1 to be the number 0 plus plus. 2, then 2 to be the number 0 plus 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 plus. You have this, you increment 0 once, increment operation, you denote it by 0 plus plus, it is equal to 1. Then again you increment 0 plus plus, that number is called 2. And if you again do it, that is called 3. Yes. I told you that when he writes these 2 dots and this way, whatever on the left hand side is something you don't know, you are going to give the meaning by this thing. This side is something you know. I mean, in our case, we wrote 0, 1, 2. So here he is saying, in other words, he says 1, because according to him, we know 0 plus plus. By axiom 1, 0, we know. Then 1 increment. I erase. No. If n is a natural number, then so is in plus plus. So this thing is given by, denoted by 1. Again, you have 2 here. 2 is 1 plus plus. Here 3, 2 plus plus. That's what it is, etc. Now here he is writing x. If he writes this thing, denote the statement x is defined to be y. Y is something we know. What is x? X is y. That is the meaning of this. You need to get used to his notation. No, this doesn't go for a long time, don't worry if you don't like it that much. Proposition, he says 3 is a natural number. So in a way it is silly, but let's go through. 3 is a natural number. You have to think this way. I mean, a guy like him, if he is proving 3 is a natural number, silly boys like us, why cannot we prove? That's how you need to think. 3 is a natural number. So proof by axiom 1, I'm not going to write. From axiom 1, 0 is a natural number. By axiom 2, 0 plus plus, which is equal to 1, is a natural number. Again by axiom 2, again 1 plus plus is equal to 2, is a natural number. By axiom 2, again 2 plus plus equal to 3 is a natural number. That is the proof. So it is little funny, but the thing is that since we know everything about numbers, why do we define? That's why we are kind of get disappointed. Now we are going to get another axiom. Axiom 3, 0 is not the successor of any natural number. Very important one. Very important one. I have not written the here reasons. I encourage you to read the book. Not very fast, but carefully. Axiom 3. What is axiom 0 is not the successor. Any natural number. Very important one. Why do I say it's very important? It's in the book. I did not write all that because I wanted to continue. 0 is not the successor of any natural number. That is, what does it mean? That is, for all, or for every n, we study quantifiers, for every n, let me write carefully, for every natural number n, n plus plus will never be 0. N plus plus will never be 0. For every natural number n plus plus is not equal to 0. So he is trying to build the natural numbers. That's what he is building. Axiom 3. That is, we have by axiom 1 and 2, 3 is a natural number. By axiom 3, 3 plus plus not equal to 0, that is 4 is not equal to 0. I guess I have missed something. Doesn't matter. I'm not going to go back and check. Anyway, 4. Axiom 4. Axiom 4 is different natural numbers important. After you studied the course, you don't have to remember anything from this chapter. Because we are studying actual analysis, then you have to remember everything. But you don't have to try to remember everything. It's naturally you will remember. No, taste of ice cream, you don't try to remember. No, let me cram the taste of ice cream. You don't do that. No, it's natural. Similarly, naturally analysis concepts go to your brain without any effort. Different natural numbers have different successes. Have different successes. Successes. Long word. Different. That is, if n and m are natural numbers, if n are natural numbers, n not equals to nm. This chapter is very important for you when you are going to study group theory, ring theory, field theory. Not the chapter, what we do in the chapter. This will be very important in that, not in analysis. Not in analysis. If n m are natural numbers and n is not equal to m, then n plus plus not equal to m plus plus. Oh. Equivalently, you can say this thing. Equivalently, same thing. Equivalently, if n plus plus equals m plus plus, then n equals m. You can see this one is the contrapositive of this one is the contrapositive of this one. No? If we have, if I can remember, he said if p, if x then y, and if not y, then not x. They mean the same thing. This is called the contrapositive of the first statement. So you need to remember contrapositive thing. I mean, axiom 4, you don't. As long as you are studying chapter 1, these are very important. After that, it may not be the case. Okay, proposition I have here. I will not write on the board. But he wants to prove 6 is not equal to 2. He is proving. Six is not equal to 2. This is a proposition. Six is not equal to 2. I am writing using the symbols. Proof, he says, to obtain a proof, he says to obtain a contradiction, assume that assume that 6 is equal to 2. What is 6? 6 is 5 plus plus. Thus 5 plus plus equals to 1 plus plus. 5 plus plus equals to 1 plus plus. Here if n plus plus equals n plus plus, then n is equal to n. Thus by axiom foo, phi is equal to 1. Hence, 4 plus plus equals to 0 plus plus. Again, from axiom 4, thus by axiom 4 again, you get 4 is equal to 0. 4 is equal to 0. Is this a contradiction?
Yes.
How do we do?
Because 4 is equal to 3 plus plus. But
Oh.
it's
So contradiction comes from there, not from here. Thus, 3 plus plus equal to 0. This contradicts axiom 3. This contradicts. Can you see already, although it looks little silly, we have proved that 6 is not equal to 2. Not only that, whatever you know about the numbers, you have to check alone. After there is one more axiom, after that you learn that axiom, you need to be able to do anything you know about the integers from that set of 5 axioms. Now we have proved that 6 is not equal to 2. Now it comes to axiom 5. Axiom 5, principle of mathematical induction. That book, my yellow book, is about induction. Principle of mathematical induction. What it says, in school you study induction, no? But you are not given the correct statement. I will write it on the board because it is important. P and B, any property pertaining to a natural number. Natural number A. Suppose that P0 is true. P0 is true, and suppose that N suppose that whenever Pn is true, Pn plus plus is true. So, the principle of mathematical induction has two assumptions. One is P0, because in his set of natural numbers he has the number 0. No, that's right. When you study in school, maybe you would suppose P1 is true, and suppose that if Pn is true, then Pn plus 1 is true. He is writing the same thing in a different way. Then Pn is true. For every natural number n. So this is the principle of mathematical induction. Let me say kind of friendly language. This is, I'm not saying this is unfriendly, but same. So what it says is actually you have a sequence in my way. Really you have for any n, you have a statement Pn. You have a statement P1, a statement P2, a statement P3, a statement P4 and so on. So how many statements are there, Abhita? Infinite, very good. There are infinitely many statements. So can we do infinitely many things in our lifetime? No, even you cannot do, even though you are very much younger than me. I have no time, I may go, who knows, tomorrow, day after tomorrow, to go. But what happens here is, we cannot do infinitely many things in life. Whatever we do is finite. This one says, now we want to prove P1 is true, P2 is true, P3 is true, P4 is true, like that we want to do. Not only to prove, but also we don't have time to say it. No? How can you say it? But to prove this thing, this principle of mathematical induction is an extremely powerful tool. Very powerful. Here it's taken as an axiom. It says Roman 1, P0 is true. In your A-level style, P1 is true, the first one in our way. And 2 is, if Pn is true, Pn is true, then we say Pn plus 1 is true. In your A-level classes, you said. Here he is saying Pn plus plus. Same thing, Pn plus plus is true. We have to prove infinitely many statements. You need to listen to me carefully. We prove P0. Thereafter, we are not going to prove any of the statements. We prove something else. If Pn is true, whenever, I have to add that word, say in other correct one, for each n, let me see, then this will become simple. We prove the zero statement, P0 is true. Or in your A-level you prove P1 is true, then you prove no matter which n you take, if Pn is true, then Pn plus plus or Pn plus 1 is true. You have proved only first one, P0. Then you conclude that all of them are. Then Pn is true for every natural number n. But you have to see the power of this principle. There are infinitely many statements to be proved. Can we do it in our lifetime? No. But here this principle says, prove the first one is correct. Then it says, take any number here he says, whenever Pn is true, that means for any n, if Pn is true, then Pn plus 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 is true. Then conclusion is all of them are true. Very, very powerful one. That's why I have written a book. Very powerful. So, anyway, for us, it is an axiom for him. Axiom 1, 2, 3, 4, axiom 5. As long as you are dealing with chapter 1, it's good for you to at least remember this 5, because you are going to use this 5 and prove everything you know. Everything you know, using this 5 about integers. Whatever you know about integers, you should be able to prove using this 5. Before a while we proved that 6 is not equal to 2. We did not need axiom 5. From the first one axioms 2, 3, 1, 2, 3, 4, we proved it. So I guess you haven't done actual induction problems in your A level, unfortunately. But doesn't matter. Let's go. So first one is 0 is a natural number. Second one says if n is a natural number, then so is n plus plus. N plus 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 never will be equal to 0. And if n plus plus is equal to n plus 1 plus, then n is equal to m. And the principle of mathematical induction. These are our 5 axioms. Now in my notes, actually you should read the book. For many of them he says the reason, he explains the reason to come up with these axioms. I didn't do it because I would like you to read, and I'm doing the essential thing. I'm taking the set, consider n dash in your notes, 0, 0.5, I'm putting 0.5, 1.5, 2.5, etc. That says n dash satisfies axioms 1, 2, 3, 4. If you put, I have put n dash to be then 0, then you put 0.5, then 1, then 1.5, then 2, then 2.5. This kind of thing. I am encouraging you to read the book because that will make your brain logical. I mean, you will not be using them after after the chapter is over. You will not do it. But to understand how natural numbers are constructed, you need all of them. It's good for you to read the book. He says n dash satisfies axioms 1, 2, 3, 4. 0 is there anyway. If n is a natural number, so is n plus plus. If you take 0, 0 plus plus is 1 natural number. If you take 0.5, 0.5 plus plus is 1.5. That is, 0 is not the successor of any natural number. Nothing before 0. And if n plus plus equals n plus plus, then n is equal to 1 is also true. However, 0.5, 1.5, 2.5 cannot be obtained from 0. You don't get 0.5 from 0. In particular, 0.5, 0 plus plus is not equal to 0.5. Therefore, n dash is not equal to n. Even though all 1, 2, 3, 4 axioms are correct, n dash is not equal to n. As a result, n has elements obtained from 0 and increment operation. That's how you need to remember. N consists of members from 0 and increment operation. Principle of induction prohibits any number other than the true natural numbers appearing in n. So it is using the word true. because of index. You need to think about this, by the way, when you go home tonight before you sleep. Because of this, why we cannot have 0.5, 1.5 like that? Spend like 5 minutes, think about it. It is like a X only if Y, that kind of thing you need to think a little bit. However, principle of mathematical induction is very powerful. It can do wonders. Amazing. Oh. Let's see whether I will be able to do someday some stuff. I say I want to do many things, but we meet twice a week. The principle of induction gives us a way to prove a property P n is true. And can build P n is true for every natural number n. As a result, you will see many proofs in the following form. I mean, he is just giving a proof. I can do one example, but let's see. Let's read this thing. What he says is, many proofs will have the following form. This is not a proof. A certain property P n is true for every natural number n. Suppose you, let's wind up a very simple one. Very, very simple one. You all can do. Very simple. Prove that. Absolutely simple. Sigma k going 1 to n is equal to n times n plus 1 divided by 2. So that I am taking, he says proposition here, certain property P n is true for every natural number n. So what I do is prove, let P n be the statement. Sigma k going 1 to n is equal to n times n plus 1 divided by 2. I said Pn is that. I want to prove this means actually sum of the first n integers is equal to n times n plus 1 divided by 2. So I want to use principle of mathematical induction. So I said Pn. So thus I want to prove Pn for every natural number n. I want to prove Pn for every natural number n. So that's why here is a certain property Pn is true for every natural number n. So according to him, we use induction. So I will say we use induction. I will also write. We use induction. We first verify the base case n equals 0. In A level, you prove this one is true for your base case is 1, P1. Here in his case he included 0. So we use induction. In the A level one, we first verify the base case n is equal to 0. Or in our case n is equal to 1. Our base is 1. So that is true P. If you add sigma k going 1 to 1 is actually 1 is equal to 1 times 1 plus divided by 2. Therefore base case is true. Right? Hence the base case. Hence the base case. Then what you do, you want to use this one. Now, what it says is, whenever Pn is true for Pn is true, Pn plus 1 is, I haven't written everything, I guess. Yeah, that's it. So, I'm going to find it. What is the time? 11, here that's the region. Doesn't matter, let me again. Pn plus is, suppose that P0 is true and suppose that whenever Pn is true, Pn plus is also true at least. Also. Very important. Whenever Pn is true, Pn plus is also true. In our case, Pn plus 1 is true. So what you do is, whenever Pn is true, you say suppose n is an integer, n is a natural number, or n, to make it short, n is such that Pn is true. We assume n is an integer such that Pn is true. Now I have to prove that. I have proved P1. Base case I have proved. Now I am saying, suppose n is an integer such that Pn is true. Then what do we know? Thus, sigma k going 1 to n is equal to n times n plus 1 divided by 2. Now we have to prove for n plus 1. Then notice that you had sigma k going 1 to n plus 1 is actually sigma k going 1 to n plus n plus 1. Right? Then this is n times n plus 1 divided by 2 plus n plus 1. So you can see this is n plus 1 times n plus 2, or else n plus 1 plus 1 divided by. Therefore, we have proved if Pn is true, then Pn plus 1 is true. Hence, by the principle of mathematical induction, Pn is true for every natural number n. Got the Buddha message? We proved, I have to prove this is for, prove that this for every, I am writing less every natural number n. I wanted to prove infinitely many statements. So I am using induction. I said let Pn be the statement, that one. Then I proved P1 is true. Then I assume that suppose n is an integer such that Pn is true. Then I proved Pn plus 1 is true. Then by the principle of mathematical induction, Pn is true for, you understand? Yeah. Every natural number n. So I mean he has a proof here. We use induction, we first verify the base case, then we assume, now suppose inductively that n is a natural number and Pn has already been proven. We now prove Pn plus plus, assuming Pn is true. This closes induction and Pn is true. In induction, we use this kind of proof so much. That's why he says, you will see many proofs in the following form. Many proofs are in this form, you will see. Now I'm kind of hungry. Yes, excuse me. So, I will give one or two exercises include for homework, so that you will get a bit of taste of course here in the book also he is using the principle of mathematical induction a lot, but they won't make you happy. There are certain type of problems that we like to solve. I will write some of them in order to make us happy. So we have 1, 2, 3, 4, 5 axioms. These are called, I have written axioms 1 to 5 are known as the piano axioms for natural numbers. Piano axioms are very famous, by the way. They are all very plausible. We shall make the following assumption. Here is making an assumption, I will not write. There exists a number system N whose elements are all natural numbers for which axioms 1 to 5 are true. It is an assumption එකක්. There exists a natural number system N whose elements are all natural numbers for which axioms 1 to 5 are true. So we are assuming that there is such a thing, axioms 1 to 5 are true. We will refer to this number system N as the natural number system. Of course, there could be more than one natural number system. However, all versions of the natural number systems are equivalent. Equivalent is the word, equivalent algebraic wise. We will not prove the above assumption. This is the only assumption we will make about numbers. But it's a big one. He says the only assumption is there is a number system for which axioms 1 to 5 are true. That is he says N. We can build all the other number systems, create functions, and do all other algebra and calculus. Whatever, of course, these are only about integers. There are other axioms for real numbers, bunch of them. So anyway, he wants to, something good is, this is the most primitive one, kid goes to Montessori. First he learns 1, 2, 3, most primitive one. So it is good that he has introduced this thing, though in a sense not that entertaining, because we like difficult things, entertaining things, but this entertains in a different way, in the sense it's a logical entertainment. Proposition here is a recursive definition. Sometimes in maths you define things recursively. Recursively means something like I get tired when I clean the board. It's very not easy. I guess these pens are not that easy manipulated. next time I will ask him. I guess this may not be the proper pen to use on this board. My shoulder is pain. What do I say? I mean, sometimes can you say, sometimes sequences you say x1 is 1, x2 is 1, then x3 is, no, xn is xn minus 1 plus xn minus 2 for each n greater than 2. You are given x1 and x2, then you say for each n greater than 2, xn is xn minus 1 plus xn minus 2. So how much will be x3 then? x3 is x2 plus x1 is 1 plus 1 is equal to 2. x4 is x3 plus x2, x3 is 2, x2 is 1. Like at once you cannot say what the formula for xn, but this way you can find any xn for any n. So this kind of thing is called, this is a very famous sequence. Have you heard of this?
No.
Very famous. 1, 1, 2, 3, 5, 8, 13. Very famous. Very, very famous. Fibonacci. Fibonacci. Fibonacci sequence. It's a very famous one.
We know the name. We know the name.
Ah.
We know the formula.
It's a very famous one. Many exercises in this book. Fibonacci sequence. So some certain, now here, of course, you can prove a formula for xn once you know how to solve difference equations. But quite often we get this kind of definitions for a sequence, so we call such a thing is a recursive definition. You know 1 or 2, then you have a relation like this. The remaining ones you can compute recursively. They are called recursive definitions. Fibonacci sequence, by the way, is a very, very famous sequence. Very famous one. Very, very famous. There are many things about Fibonacci sequence. So someday when we are doing sequences at university, I get very tired, don't leave me. Maybe I should change the pen to that.
Like Atlas one?
Huh?
Does Atlas do one?
This one? This one? This one? I have to buy another one. Show it. I will write on the board, this is on page 6, proposition recursive definitions. This is the idea, the one I wrote. Here he says, suppose for each natural number n, we have some functions fn, you know the word function, no? Fn, going from n to n. That means you have f1, f2, f3, f4. Like this you have functions, a sequence of functions. For each natural number n, we have some functions fn into n from the natural numbers to the natural numbers. Let C be a natural number. Simple C is a natural number. C is a natural number. Then we can assign a unique natural number an to each natural number n such that a0 is equal to C, an plus 1 is fna. Then you see, you are given the f1, f2, f3, f4 functions. You have given a number say fn is going from n to n. So we are defining a0 is equal to C. Then we are not defining a1. What is it? a2. So what from here? a0 is equal to C. We are defining this way, like the way I wrote Fibonacci sequence. Then a0 plus 1 is f1 of f0 of a0. That is a1. a1 is f0 a0. This way a2 is f1 a1. a3 is f2 a2. Can you see? So first one is given, the other ones you have to recursively apply. You get a1, a2, a3 and so on. So this is a recursive definition. When you are studying, we are in an analysis class. Analysis classes are full of sequences of functions, sequence of numbers, so on. So recursive definitions are there everywhere. Then we can assign the natural number a. Here he has a proof, but we don't need the proof. Still I will read it. We use induction. We first observe that this procedure gives a single value to a0. By this method you get, it is given a0 equals C0. There is nothing else for a0. So it is clear. Namely C. None of the other definitions an plus 1 equals fn an will redefine the value of a0. Can you see here? You are given a0. By this thing you will not get again a0. Never. That's what he is saying. Never. Because he says because n plus plus. I haven't written this on the board. No? Let me see. And see. a0, an plus 1. I go to my familiar place, n plus 1, but he has written n plus plus. None of the other definitions, an plus 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 fn an will redefine the value as 0 because n plus plus will never be 0. N plus plus will never be 0, therefore from this one a0 will not be defined again. Now suppose inductively that procedure gives a single value to an. He is using this principle of mathematical induction. Then it gives a single value to an plus plus, namely an plus plus is fn. No need to write even an plus plus is fn an. So you get only one. None of the other definitions. An plus plus fn an will redefine the value of an plus plus because if n is not equal to m, then n plus plus not equal to m plus plus. It's good for you to read the book bit carefully. Otherwise, no need of reading. No? None of the other definitions, an plus plus fn an will redefine the value of an plus plus. Because if n is not equal to m, then n plus plus not equal to m plus plus. This completes the induction. So an is defined for each natural number n with a single value assigned to each an. I mean, it is very clear, but either read this one or actually I am writing many things I am writing from the book because this is a new way of writing also in this case. So, I mean, recursive definitions are all over, everywhere in analysis. In algebra, I mean, it's not that much. You have axioms 1, 2, 3, 4 are kind of in the same boat, no? Same line. Axiom 5 is the principle of mathematical induction. Somehow, I hate to say this thing, this can be proved. Then you may have, if it is an axiom, how can you prove? Because assuming some other things, in this book, there are 2 or 3 proofs about principle of mathematical induction. Then assuming some other things. That is how. So that's why I told you, these 4 are in this one set of axioms and this one is separate one. This is separate, principle of mathematical induction. But I will include some good problems, good for you to try induction problems. I will put some of them in your tutorial. Dr. Rabat told me, give them 20 problems each week. I don't know, because this 20 is easy. Logic, no? When it comes to actual analysis, I don't think you can do 20. Can you?
We don't do analysis, so our process is
it will be difficult. But because you are very young, however, you can try hard. Let's see anyway. So we have time. We have time to discuss about. So I am going to erase the board again, emphasizing 1, 2, 3, 4 axioms. You have to remember them separately. Axiom 5 is actually the principle of mathematical induction. So I don't know why it was labeled as axiom, but it's okay because the reason is in principle of mathematical induction is proved assuming other things. Here in this case, it is an axiom. So maybe what I have assumed to prove this can be proved using this conversely. It could be. So I'm going to. Okay, now remember, all you know is about the numbers, you have to be careful. You have 0 there, increment operation there. Then you have these 5 axioms. Last one is actually principle of mathematical induction that you heard in your A level also. Now we are going to talk about addition. Addition. Only addition. No subtraction. So you need to be careful. Definition. Addition of natural numbers. I'm not right. Let m be a natural number. Can I write this way? Let m belong to n. That means let m be a natural number. To add 0 to m, I have to write to add 0. Oh, sorry. Come on. 0 to m. We define zero plus m. You need to remember, Buddha, look at the word. You are adding 0 to m. This is not m to 0. To add 0 to m, we define, we are adding 0 to m. Not m to 0, very important. 0 to m. and answer is M. This is definition. M is a natural number. To add 0 to M, we define 0 will be added to M, and I put this same notation to make sure it is addition. Now suppose inductively that we have defined how to add N to M. Induction style over there, whenever we is true. Suppose we know how to add, let me write in colloquial English, suppose we know how to add N to M. That means, in other words, we know answer for this, how to do it, we know. Then we can define N plus M. And you see then, because it is a definition, I put it that way, N plus M is N plus M plus. Assume we know how to add 0 to M, not M to 0. 0 is in the left of M, 0 to M, answer is M. It is like P0. Then, suppose we know how to add N to M, we know this somehow, we know it. Assume. I said, suppose using that, we define how to add N plus to M. It is, since we know this, we know the answer for this, plus. That is the definition. By defining this. Hence, so this is the definition. Hence, we know right away 0 plus M is M. 1 plus M is 1 plus M is 1 is 0 plus 0 plus M. We don't know how to add 1 to M, but we are going on using induction. This by definition is 0 plus M is 0 plus M plus is M plus. Can you see? Now, you cannot write here, you cannot interchange anything. Only thing you can assume about natural numbers is 0 is there, increment operation is there, 5 axioms are there, nothing else, you don't know anything else. 2 plus M is 2 is 1 plus M, by definition is 1 plus M plus 1 plus M is, you have 1 plus M is M plus, then plus, and so forth. So far you don't know M plus 0. You don't know M plus 0. Because when you are going to study group theory, it's very important. A plus B and B plus A can be different. Even in matrices, you did matrices, then A times B is not equal to B times A. It's simple. Notice that our definition of addition is recursive. This is recursive because we cannot define right away. By one line we cannot define how to add numbers. We are going recursively. This one. You know how to add 0 to m, and you inductively assume that you know how to add n to m, then you are defining how to add n plus plus to m by n plus m plus plus. Note that our definition of addition is recursive. Observe that given a natural number m, we have defined n plus m for every natural number n. This way, because this definition is recursive, for any n now we know how to add n. We know how to get this answer, going recursively many times. Given natural number m, we have defined n plus m for every natural number n. Here we are specializing the previous general discussion to the setting where an equals n plus m and fn an is a recursive definition. We are saying this is compatible with it. This definition is asymmetric. 3 plus 5 is incrementing. 3 plus 5 is incrementing 5 3 times. No? 3 plus 5 is 2 plus 5 is 2 plus 5 plus, then 2 is 1 plus 5 plus is here 1 plus 5 plus, then plus 1 plus 1 is again 0 plus 5. I'm getting tired. You know what I'm doing, no? What I'm saying is, where am I? 3 plus 5 is incrementing 5 3 times, while 5 plus 3 is incrementing 3 5 times. 2 different things. Luckily we get the same answer anyway. 5 increment 3 times, certainly they both yield the same value, 8, regardless of the fact that they get the same value. What we are doing is different, according to his definition. Prove that sum of 2 natural numbers is again a natural number. Because we don't know. Prove that sum of 2 natural numbers is again a natural number. We have 2 facts about addition. What are they? 0 plus m is equal to m, and n plus m is, you need to, as long as you are doing chapter 1, you need to remember these 2. What we know is, we are told this is the definition. 0 plus m is m, n plus m is n plus m plus plus. Here, assuming that we are in the inductive recursive definition, assuming that we know how to add n to m, we have defined how to add n plus to m. So, using that, we have 2 facts about addition, that 0 plus m is equal to m, and that n plus m is n plus m plus plus. Remarkable, this turns out to be enough to deduce everything else we know about addition. Let me read it again. Remarkable, this turns out to be enough to deduce everything else we know about addition. By these 2. That's what it says. Remarkably, I am reading it again. This turns out to be enough to deduce everything else we know about addition. From these 2, whatever we know can be deduced. That's what it says. This pen is good. Can you use? I don't have to good time. For any natural number n, this is a good one. For any natural number n, n plus 0 is equal to n. We don't know it. For any natural number n, n plus 0 is equal to n. Proof. We use induction. The base case 0 plus 0 equals 0. I don't have to write, no? So you have the note, no? Have I given you page 7, etc.? I have given you only up to 6. Then 7. Just take these two. 7. See, remember, you know this line 0 plus m is equal to m, and if you know how to add n to m, you know how to add n plus to m by this line. So this is a recursive definition. So now we are on the way to prove that n plus 0 is equal to n. We are going to use induction. Then I have to prove that 0 plus 0 is equal to 0. Kuta, ask. How do I know 0 plus 0 equal to 0? How do you say? Maybe Kuta, can you? You Kuta, what?
By definition, 0 plus n equals n for any natural number.
Here, I mean, though I wrote 0 this place, when I write, I can say 0 is in the second place. That's what here, if you put 0 here, if you add 0 to 0, you end up with 0. If we are starting monoids and so on, this part is very good, very helpful for you. Logical argument. You understand that I have written down 0 plus equals 0. So we are done with the base case. Now suppose inductively that n plus 0 is equal to n. I am not writing the proof because you have the notes. We are assuming, I write, assume, let me write. N plus 0 is equal to n. Now I want to show that n plus 0 is equal to n plus. Let's see whether we can get it. I have proved 0 plus 0 is equal to 0 using this one. Now I am assuming n is an integer such that n plus 0, n is a natural number such that n plus 0 is equal to n. I want to use in these two or other things that I have done earlier. I want to prove n plus 0 is equal to n plus. However, n plus 0, by here it is n plus 0 plus plus from the second one. I am assuming induction hypothesis n plus 0 is equal to n then plus plus. Proved. You understand, Pata? So he says this closes the induction. Now let's do one more. Lemma 2, this is lemma 1. Lemma 2, for any natural numbers n and m n plus m plus plus equals to n plus m plus plus. We want to prove for any natural numbers n and m, n plus m plus plus is equal to n plus m plus plus. Let's see again. We prove, we induct on n keeping m fixed. We keep m is arbitrary but fixed. It won't change. So now the base case. Let's see whether we can prove it. We fix m and n goes 0, etc. So base case, we have to prove. I am not writing complete proof, just important lines. We induct on n, so we have to prove 0 plus m plus plus is equal to 0 plus m plus plus. This is what we need to prove. 0 plus m plus plus is equal to 0 plus m plus plus. If you look at the first line, 0 plus m is m by definition. Therefore, by definition, 0 plus m plus plus is m plus plus. By definition, 0 plus m plus plus is m plus plus. And by definition, 0 plus m is equal to m. Here 0 plus m is equal to m. Thus 0 plus m plus plus is equal to m plus plus. So we have shown that 0 plus m plus plus and 0 plus m plus plus both are equal to m plus plus. Therefore, base case is proved. Base case is proved. Both sides are, I have written here, but by definition 0 plus m plus plus equal to m plus plus and 0 plus m is equal to m, so both sides are equal to m plus plus and thus equal to each other. So base case is done. Now we assume inductively we are going to prove m plus plus is m plus plus. So base case is done. Now we assume, I will write only this part, assume n plus m plus plus is equal to n plus m plus plus. I am just assuming this because I am going to use, my m is fixed. I am inducting on n, sorry, I did a mistake, made a mistake. Assume n plus m plus plus is n plus m plus plus. I am assuming we have to show, need to show n plus 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 m plus plus m plus plus m plus 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 m plus plus. This is, are you with me? Yes. I want to prove this is n plus 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 m plus plus is n plus 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 n whole thing plus plus. Uta, you follow? Okay, then let's see. So left side is equal to this side LHS, left hand side is equal to from here n plus 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 m is n plus m plus plus. So if I use that, this one is equal to, left hand side is equal to n plus m plus 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 plus. Right? Did I do something wrong? N plus m plus 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 plus. By definition of addition. These are the two things, no? 0 plus m is ma. If you know how to add n to m, then n plus plus m is like this. Then this side n plus 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 m, this one n plus 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 m is again by this line n plus m plus plus n plus m plus plus by the definition of addition. And here n plus m plus plus. So many plus signs I get confused. This is little fun. N plus plus m is equal to n plus m plus plus by the definition of addition. So the right hand side is equal to, right hand side this. So right hand side is equal to, so right hand side is equal to n plus plus m plus plus, m plus m plus 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 plus. Right hand side, this one. Left hand side, however, n plus m plus plus, by inductive hypothesis, n plus m plus plus is n plus m plus plus. Then plus plus. So both left and right, you will get n plus m plus 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 plus. Somebody may think these people are loose, no? Okay, so anyway, we proved that lemma 2, I guess. So it has a logic. Now we have to prove that for every natural number n plus plus equal to n plus 1. I guess he hasn't proved it in his notes. I guess he is asking why. I guess I thought of writing the proof. Don't take anything for granted when you are doing pure maths. Tiny little thing can be a very serious thing. That's how I learned pure maths. Some people, oh, it's nothing, oh, that's true. No, prove it. That is the way to learn pure maths. Corollary. Yeah, corollary. For every natural number n, n plus plus is equal to n plus 1. Ayyo, I erased the what is it? 0 plus m by definition is m, no? What is the other thing? If you know how to add n to m, then n plus 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 m was n plus m plus plus, ne? Correct? Okay, so I say since 0 is a natural number, by lemma 2, proof. I guess in the book, he says this thing and asks why. So I thought of writing the proof. That's my memory. He is asking why it is. Somewhere I can. Doesn't matter. Anyway, let's prove it. No? Since 0 is a natural number, Uta, can you tell me the proof? N plus plus is equal to n plus 1. Anyway, let me write. Since 0 is a natural number, from lemma 2, from lemma 2, we have lemma 2 over here, n plus n plus plus, n plus n plus 0 plus plus, n plus 0 plus plus, right, is equal to n plus 0 plus plus. N plus 0 plus plus. However, we know n plus by lemma 1, n plus 0 is n. So This is n plus plus. Right? By lemma 1. Both lemmas are used here. By definition, somewhere we wrote one is equal to 0 plus plus. We define that way. 2 equals 1 plus plus. So then we are done, no? N plus 0 plus plus is n plus 1 and 1 plus 0, 1 is equal to 0 plus n plus 1 is equal to n plus plus, right?
Yeah.
Okay, now these are doing these kind of things will help for algebra, not for analysis. Addition is commutative, good one. Addition is commutative. For that means for any natural number n and m, numbers, I guess, no, for any natural numbers n and m, n plus m is m plus n. Again proof, we will use induction. We will use induction. On n, again, keeping m fixed. We are inducting on n, keeping m fixed. Base case, you want to prove n is equal to 0, no? Base case, you have the notes where there's we need 0 plus m is equal to m plus 0. I want to prove this. 0 plus m is equal to m by definition. M plus 0 is equal to m by lemma 1. Therefore, this base case is done. That's the base case. Puta, you follow, no? No, he is more aggressive now. He is invited to lunch now. Now, lunch begins at 12:30. I guess he will be at the hotel at 11:30. That's the base case. When I said thus, because 0 plus m is equal to m by definition and m plus 0 is equal to m by lemma 1. So that's the meaning of thus here. Now suppose inductively that n plus m is equal to n plus m. Inductively, so I am just writing one word, inductively. N plus m is equal to m plus n. Assuming this. Now we have to prove that, need to show that n plus plus m is equal to m plus n plus plus 2 Yes, sir. Need to show this thing. N plus plus n. We proved it for 0. We are assuming for n plus m is equal to n plus n. Now we need to show that n plus 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 m is equal to n plus n plus plus. By definition, n plus plus m is equal to n plus m plus plus. No? N plus m plus plus. Again by lemma 2, it says n plus m plus plus n plus plus n plus n plus plus. By definition, n plus plus m is n plus n plus plus. By lemma 2, n plus what? I'm being silly, I guess. So many classes, no? M plus n plus plus m plus n plus plus m plus n plus plus by lemma 2. Now we are done because here n plus plus m is n plus n plus plus and m plus n plus plus is m plus n plus plus. However, by inductive hypothesis, n plus m is equal to m plus n. Okay, alright. So we are done. These two are the same by inductive hypothesis. So we are done with that. Puta, you are with us, right? I know now you are with us because of the lunch. Otherwise, you are late. Now, you won't do that. So we are in the process of justifying 5 axioms are enough. I cannot say enough. 5 axioms with the help of 5 axioms, the things we know can be proved. I cannot use the word enough. Who knows whether you can reduce 5 to 4? You don't know. When you are doing group theory, you run into that kind of questions. Proposition addition is proposition. Addition is association. We have the 5 axioms. We are proving the things we know about numbers, natural numbers. The results we know can be proved using these 5 axioms. That's what we are doing. For any natural numbers ABC, for any natural numbers A, B, C, we have A plus B plus C is not equal to A plus. No, it is equal to A plus B plus C. So after proving this thing, you don't have to put parentheses. Or whether you add first two and the third one, or whether you add last two first and then add A to it. Answer remains the same, but these are not true for vectors. You know, so many things, these are not true. Oh, I haven't proved it, by the way. I said proof is exercise. You will be able to do it, will you? If you couldn't, let's do it together. Maybe I got tired. Actually, I get tired, plus. Yeah. I got stuck in something. I had a little hard time to do it. Something, I cannot remember what it is. Maybe I can. Interesting. Prove that we have come there. Suppose n less than or equal to m. Prove that n equals m or n less than m. I got stuck in proving it. Serious. Anyway, you will get it as a tutorial problem. I don't know whether now I can do it again. I did not write down the proof, but I managed to do it. So addition is associative. I guess he has put this in exercises, no? Because of this associativity, we can write sums such as A plus B plus C without having to worry about which order the numbers are being added together. Cancellation law, that's a good one, by the way. Proposition. Cancellation law. These are exactly like your abstract algebra. You are doing use monoids and stuff. These are in algebra, not in analysis. But anyway, let A, B, C be natural numbers. Such that A plus B is equal to A plus C. Then B is equal to C. Then B is equal to C. A, B, C be natural numbers such that A plus C then B is equal to C. Did you notice something? So far we don't have minus. Because you cannot say, let's subtract minus A from A from either side. You cannot do that. That's the thing about proof. Again, we prove this by induction on N. Induction on N. Induction on A. Okay, let's see. First consider the base case. A is equal to 0. So, Then we have 0 plus b is equal to 0 plus c. We want to show that b is equal to c. But by definition 0 plus b is b. Again by definition 0 plus c is c. 0 plus c is c. Therefore b is equal to c. Best case is done. Now suppose inductive will be that a plus b. Now suppose inductively that a plus b equals a plus c implies b is equal to c. Assume that. I have not written everything here. I am assuming a plus b is equal to a plus c implies b is equal to c. We want to prove that cancellation law. We want to prove that a plus b. We want to show that. We want to prove. We want to show that a plus so many plus signs. We want to show that a plus b is equal to a plus c implies b is equal to c. That's what we want to prove. No? So if you want to prove this thing, so assume this one. No? Assume a plus b is equal to a plus c. Assume this. A plus b, this thing is a plus b plus plus. From here, this one is a plus c plus plus. Then 2 plus, this plus is equal to that plus, therefore a plus b is equal to a plus c, right? M plus plus equals n plus plus implies m is equal to n. Now we know that for a, by inductive hypothesis, a plus b equals a plus c implies b is equal to c. By induction hypothesis, by inductive hypothesis, b is equal to c. So, in a way, nice. So we proved it to that, right? Okay. Now, if something comes to your head that we should prove, only with addition, however, no subtraction, see whether straight down and see whether you can prove it. So this makes your brain logical. Plus, you are learning these 5 axioms are enough. However, principle of mathematical induction is there. It is not one axiom, it is 10 million axioms. Isn't that we are doing? So that is nice. Now we are going to define positive natural numbers. I suppose we are not in a positive situation to do it. Positive natural numbers. Where is it? 10, 11, 12, 13. So, because it is a new thing, again his definition only. For a second, let's talk about his definition. A natural number is n is said to be positive. He says n is positive if and only if n is not zero. That is his definition of n being positive. Is not equal to zero. So according to his set, it is trivial. No, his set is n 0, 1, 2, etc. If it is positive, other than 0, other numbers are positive. Except 0, other numbers are positive. Therefore, definition. That is also very important, by the way, when you are doing pure maths. When you get the definition, see whether it is close to your heart. Otherwise, you will find it difficult to work with it. If you don't, oh, this definition I don't believe, no, then you will find it difficult to cope up with it. You need to make sure you get the feeling of definition that is close to your heart. And when you see axioms also, you need to ask yourself whether it should be an axiom. That's important. So anyway, then let's quit for the day, no? Now it is 1, 3 or 4 minutes.